Hi there, welcome to another presentation on the principles of operating systems. My name is Emmanuel Doywood. The course material we'll be using for operating system would be Operating System Concepts, the 10th edition by Silberchers, Galvin, and Gann. Other suggested books include Modern Operating System by Tenenbaum. And then we also have Operating System Principles and Practice by T. Anderson and M. Darling. Our course content will be looking at introduction, which has to do with introduction to operating systems, computer system structures, operating system structures, process management. We also look at deadlocks, look at storage management, where we'll be discussing about different types of memory management, such as paging, segmentation, and virtual memory. We'll also look at file system. In file systems, we'll be looking at file system interface and implementation. They also discuss input-output subsystems. Now, the objectives of this course is to know what an operating system is, look at operating system histories from simple batch systems to multi-program batch systems, time-sharing systems, and personal computer systems. We'll also look at parallel and distributed systems and real-time systems. Firstly, what is an operating system? An operating system is a program that acts as an intermediary between the user of a computer and the computer hardware. We can also define an operating system as a program which acts as an interface between computer system users and the hardware and provides a user-friendly environment. Now, the major cost of general-purpose computing is software, because to build a software is expensive, and most times you may have to build a software that works and understands the hardware. So if we have to designing different application programs that will have to understand every hardware is going to be installed on, will be tedious. So the operating system simplifies and manages the complexity of running application programs efficiently. So you can put in the application, install it in the operating system, and then the operating system will talk to the hardware and allow you to be able to run the application with ease. Now we have different components of the computer system. We have the hardware, which provides the basic computing resources such as the central processing unit, CPU, memory, and the I/O devices. And also remember that on the hardware, we have the operating system. It controls and coordinates the use of hardware among application programs. So we also have the application programs which solve computing problems of users. For example, we have application programs that are compilers. We have the ones that are database systems. We have the ones that are video games. We have the ones that are business programs, such as banking software. Now, all these applications, these video games and databases, has to be installed into the computer system. But most times, they cannot directly talk to using the low-level language of the operating system, of the hardware. So the operating system has to be the intermediary that links the application programs to the hardware. Now, users are also part of the computer system because people use the application programs to do some work. Sometimes machines are operated using computer systems, and sometimes other computers also. Let's have an abstract view of a computer system. Now, the way it works is that user one, user two, different users, multiple users can have multiple applications. Now, the applications talk through the system and application programs, such as the compiler that turns the high-level language, compiles it into a system program. Assembler also does that. It assembles. You have text editors, you have database systems, all of them. The system and application programs all are within the higher layer, and all of them are installed in the operating system. So it's the operating system that actually picks up whatever information sent from the application program and gives it to the hardware. So the hardware now runs and executes it and gives needed output. The operating system can be seen in different forms. Several views have been used to look at the operating system. You can look at it in different ways. Like we can say it is a resource allocator. It's a resource allocator because the operating system allocates resources such as software and hardware to the computer system and manages them efficiently. So it allocates resources such as the central processing unit. So it allocates resources such as the input and output devices. So any this resource that needs the operating system definitely is being handled by any application that needs a resource. Such resources are being given out by the operating system. It also acts like a control program. The operating system acts like a control program because first and foremost, it has to come down and controls execution of user programs and operation of I/O devices. So it controls the execution of every program. It has to give it time, how long it's going to stay, and when it should stop. So any process, any program that is executing, the OS is aware of it. Now, the operating system acts within the kernel environment. Now, the kernel is where the instructions can be given directly to the hardware, and only the operating system has that access. So the operating system is the program that executes forever. The program that executes forever is the kernel. Everything else is an application with respect to the kernel. The program, once you boot the system, the kernel comes on and stays on. So an application wants to print, it sends information, and then the kernel can print it. Then the program can shut down and go. Another one needs to send information, store information in the hard drive. The kernel of the operating system handles all that. The operating system also has several roles. It's also a referee. It's a referee within the computer system because the resource allocation among users and applications are being managed by controls. It make sure that nobody uses something to cheat the other process or the other. Yes, the process must have equal or properly arranged time in which they should operate and when they should stop. The isolation of different users, applications from each other, that's what it does. It separates all of them. Different users work in their own environment, applications work in their own environment so that there's no crash or clash between the different applications. It aids communication between users and the applications. Now, the reason also acts like an illusionist. Each application appears to have the entire machine to itself. Infinite number of processors, near infinite amount of memory, reliable storage, reliable network transport. So we sometimes think as if you can open multiple programs on a system and it looks as if the many programs that you have opened are all working with different processors and different memory. But no, it's your operating system that does that. It allows all the programs to work using one system and it shares time to each and every one of them. Now, even in a distributed system where many people are connected to one system, the operating system can just create that environment. You feel that you're just the only one working on your own system, whereas every user is sharing a hard drive, memory, or sharing a processor. Now, it also acts like the role of the operating system also has libraries, user interface widgets. You reduce the cost of, also reduces the cost of developing software, because anybody that develops a software may have had to primarily think of how he's going to talk to the hardware by himself. And that is very tedious and a lot of work. But once you have the operating system, all you do is just mind what you are building, like a banking software, just build that. And then everything you need to do is just put the call to call, monitor, or the mouse. You don't care about the mouse when you are building your software. You don't care about the screen being on or off when you're building your software. You don't care about the printer. You just build your software and allow it, and the operating system handles the rest from then on. Now, we also have example of a file system. Now, let's see, we had a file system. We have operating system here. Referee prevents users from accessing each other's files without permission. That's what a referee does. The illusion is files can grow nearly arbitrarily large. Files specific in the machine in the middle. And we also have some of the directories, name directories, and now the goals of an operating system. The main goal of an operating system is to simplify the execution of user programs and make solving user problems easier. That's the main goal. It uses computer hardware efficiently and allows sharing of hardware and software resources. So every software we have to share and hardware resources are available to share. The operating system makes it easier for all parties to share that with ease without having any problem at all. Now, also, the operating system make application software portable and versatile. It provides isolation, security, and protection among user programs, as I've said earlier, and improve overall system reliability. Now, once the operating system is there, it's already been built to be able to work with the system efficiently and to secure the system. So your application can't break the system. You build your application, it won't break the system. Operating system that has been built to become more robust, that even sometimes attacks on the system can't even break the system. Even if we have antiviruses are there in the system right now, and that can stop systems from being corrupt with ease. All right. Now we have also that reliability encourages error confinement, fault tolerance, and easy reconfiguration of the operating system if need be. If in the worst case scenario, one thing we know about the operating system is that all it can do is that it can, in the worst case scenario, all right. So why study operating systems? Well, as somebody who is interested in technology, in tech, or in computer systems, you need to understand interaction between the hardware and the applications. New applications, new hardware are everywhere nowadays. So you need to understand, how the two function. You need to understand basic principles in the design of computer systems. Now, the basic principle of computer systems, how do the software talk with the computer systems? Efficient resource management, security, and flexibility has to be things that should be properly understood. Then we also have that the increasing need for specialized operating systems are happening every day. We have newer things coming out. For example, we have embedded operating systems for devices, cell phones, sensors, and controllers. We have real-time operating systems for aircraft control and multimedia services. So we need to understand our operating system work so that we can, make them better or build newer ones. Now, this is a traditional computer system architecture. You have the computer system, and that computer system has CPU, central processing unit. It has the memory, where it stores data in the disk. It has the printer controller. It has the tape drive controller. You have the memory controller, and then you have the main memory itself. Main memory is not what we call the RAM. Remember, we also have system bus that connects every part together. This is the main architecture of the system. And each of these resources must be properly handled by the operating system. Over the years, computer systems have been used for diverse things, and from military to non-military activities. And now we have gone into an era where technology keeps improving. For example, we have this man over here. Let me get. He's here. We can see him with his military gear, and he's doing things, writing something on a computer here, and he needs all this to survive in the military field. We have a server center here where you have multiple servers and computers in the data center. Now we have divers who are wearing completely computerized suits with virtual displays. They have CPUs attached to their tanks, oxygen tank, and all that they know what they're doing. Then we also have in the industry where we have people that are fully computerized. They wear wearables on their bodies so that they can detect radiations within the environment or whatever is supposed to be tested for. We also have cell phones here, where we now have wireless communication between ourselves and whoever we are discussing with. Then these are chips, and they are getting smaller and smaller over time. This is a chipcon CC1000. They get smaller and smaller, as small as the size of a coin. And we have people who are going for exploration. They also need computers, systems, which they use for diverse activities in the military, in the Air Force, in NASA, and in space. We have these also in vehicles. Now we're using autonomous vehicles, and in autonomous vehicles, we have sensors on the vehicles all around, all the sides in front, and then we have antennas all over, sensing the environment and making sure that the vehicle can move from one place to another without having a crash. We have automated vehicle checking here in some areas where they are being used to check if vehicles have been have paid their tickets or renewed their licenses and all vehicle documents before they can keep moving. We have them in the power sector. You have a smart grid here, where houses are being controlled and bills are being sent straight to the houses with ease because of they are fully or computerized and automated. All right. So we have hardware has increased so much over the years. Using Moore's law, Moore's law said that transistors will grow 2 times every 1.5 years. So the number of transistors in a chip increases twice every 1.5 years. And it's been seen that over here, that since 1975, we had 8080, which had about 10,000 transistors in there. It kept rising until around 95, we had about 10 million transistors. 10 million transistors in the micro 2000 computer. And it was much faster, much faster. About 500. The speed was much faster than what it was before. So over time, the systems have moved. Now we have Intel multi-core chipsets where we have up to i5, i7, different levels. Then we also have that growth. So we have seen the growth here right from 1978, moving 2006, we moved so high on this graph here. All right, so the president needs to keep pace with the hardware improvements, because as the hardware keeps rising and rising and rising, seeing all those years, we have seen a big difference. So from uniprocessor speed, where we had to move in large millions of instructions per second, so much, the speed was so much. We moved from 1 to having over 2,500 instructions moved being executed in 1 second. The CPUs moved from 1 CPU per computer to more than 10 in 2014. The microprocessor was moving, the cost reduced so much from 100K in 81 down to $0.20 within 81 and 2014. Okay, the RAM size increased so much. The disk capacity, now we are using what we call the SSDs. So we have newer technology that can store up to large terabytes in disk. As at 2025, we can store more than 20 terabytes in one solid state device, SSD. Our home internet speeds have increased so much over the years, from around 300 bits per second to now we are flying in gigabytes per second in after 2025. Then we have much differences. Ratio of computers, users to computers has gone so much. Now we are using one user to several computers. Before it was just 100 people to using one computer. But as at now, one person could have a laptop, desktop, a mobile device, an iPad, whatever. So watch, digitalize, so, and then individual now moves around so many devices. So the software also, the complexity of the software had also had to increase. Millions of lines of source code had been created over time, from back in the days, the shuttle or NASA space shuttle. We now have Windows 3.1, and you can see it rise from virtually just 3 million lines of code to now, as at the time Vista came out, they had more than 50 million lines of code in the software. So it got more complex and more complex, and technology kept moving. So people have also increased, you have people per computer per year. People have increased so much. We have seen from the days of the big massive computers having big transistors where you could have just one computer in an entire institution. It got smaller and smaller and smaller over time, that now we have so much more microchips that everybody has a phone, everybody has a laptop, and everyone can stream information directly from their phones, their devices, everywhere. So the technology has gone so far. Now, the operating system monitors, has monitors and small kernels. Okay, operating system, let's look at the spectrum. We have the monitors and small kernels, special purposes and embedded systems. So these are special purpose and embedded systems where we have small devices that have small kernels like uh, sensors. They have small kernels and they monitor the environment and send signals. We have satellites in space that are sending signals every day and telling the weather, right? And telling the weather and telling the where we are at any time. Now we look at the operating system has batch and multi-programming. Now in batch programming, one process is finished first before the next process is picked up. But in multi-programming, one process can be executed and then given some other task to do while another process is being picked up. So you could have multiple processes that are running at the same time, or should I say at close intervals together. Then we have time sharing, where a system shares time for every activity. For example, in work sessions, servers, mini computers, and time frames. They have a time frame for everything. So if a process is running, you can have 2 or 3 processes appearing to be running together. For example, your application, your video is running, the audio is running, and they appear to be running at the same time, whereas the computer is actually sharing time between those 2 resources. But because the computer system is super fast, it appears to us as if they are working together, because they'll be working in micro or nanoseconds, microseconds. Then you have transaction systems, which many of us are used to, where we have things like in the banking sector, we have in business centers and all that. We have personal computing systems. We also have mobile platforms and devices where we all use. These are the different things that the operating system has advanced over time. It moved from just having a small kernel to having very large kernel, massive operating at personal computing level, and when we have mobile devices where we have powerful phones and parts and other stuff being used with operating systems. Now let's look at a brief history of computer systems. Now the early systems, where we also call them the bare machines in the 1950s, were just, as you've seen them, big mainframes. Here the hardware was expensive. Human labor was even cheaper. Because at this period, human labor was cheaper. Here the machines were large. They run from consoles where the screen was just black screen, and then you had to type whatever command that needed to be done. They had single user system. They had a programmer or a user as the operator, and then you had a paper tape or punch card as the input output devices. You had to push in one of those punch cards, and then that would be read, and then whatever calculation needed to be done would be done and output be delivered. Then the early software by then were assemblers, compilers, linkers, loaders. They have libraries of common subroutines. Those were just the early ones there. Then it had secure execution, but it was inefficient use of expensive resources. Inefficient use of expensive. For example, it had low CPU utilization. You could run a computer and it could take hours just to compute simple addition of amounts of money that was being used, maybe we're trying to do an accounting stuff for a firm. It was easier to even run it, let human beings sit down and run it, add, compute, and subtract the values of the transaction than putting a computer system. It had high setup time You have to wait for the system to boot so long before it comes up. Then in the 60s, there was the simple batch systems, and that was better. You had reduced setup time by batching jobs with similar requirements. So by this time, you could have jobs that are similar could be run at the same time. So the system could kind of multitask in a way. You add a card reader, you hire an operator. So here the user is not the operator. You just go and sit down, hire an operator to help you execute it. You just set it down and it can go away, and then you wait for your outcome. Automatic job sequencing forms a rudimentary operating system. So here we had a resident monitor that holds initial control transfers to job and then back to monitor. The problem here was that you need to distinguish job from job and data from program. You need to distinguish the job from a job and data from program so that there will be no confusion. So when the program is first of all installed in the system, you now put the data which the program will pick up and then execute. Those were some of the problems it had. It had many other problems. It used to be hot. Then we now had supervisor operator control. An example is the IBM 7C94. You had secure monitor that controls job processing. It has special cards that indicate what to do. All right. And then the user program prevented from performing IO. So it was more secure. Then you had separate user from computer. The user was separated from the computer. A user submits card, dead, cards is then put on tape, the tape processed by the operator, then the output on tape and the tape printed on printer. So the parts were now different. All right. But its problem was one to still had long turnaround time of up to 2 days, right, before you could get an input and output from what we have done. It has low CPU utilization. IO and CPU could not overlap. You had slow mechanical devices. Those were some of the problems. Then what was the solution? The solution was to speed up IO. And how do you do that? By having the input outputs offline. So we have offline processing. We load jobs into a memory from tapes, card reading and line printing are done offline. So the jobs were put on tapes, okay? Load jobs from tape into memory. And load jobs into memory from tapes, okay? And then the system can now pick them one by one and be processing. So you don't really need to be there to wait for it to be ready. You can load up, you can set up a batch of work and it does that. Then you also had spooling. In spooling, you use disk. It was supposed to be a random access device. That was the beginning of RAM, random access memory. So you use disk as large storage for reading as many input files as possible and storing output files until output devices are ready to accept them. This allowed overlap because the IO of one job with computation of another. So you could see here, you could have like a job pool kind of, had lots of jobs where are stored on a disk. So that disk will be read. Lots of inputs are stored on that disk, and that disk will be read as it spins, as the storage device, is being read, the input is being gotten, and then output devices, they are being written, processed, and then given to the output devices, like printed. All right, so you have jobs coming either on the disk is being read, execution being done, and then it's being printed, the output is being printed out. All right, so now you could have an input job and an output job going on at the same time. That was the beauty of it. IO of one job with combination of another. So while one is processing, the other one is printing, and have overlaps. So now this will introduce your notion of a job pool that allows your operating system to choose between next job to run, so as to increase the CPU utilization. So more jobs could be processed. All right. So this was how they were trying to solve the batch system where you have to finish one job and wait for the next job. It was just to try and see if we could speed up the input-output system. But that definitely was not really a solution, right? So speeding up I/O demanded some new things. For example, we needed a direct memory access. So this is where the concept of the RAM came in, the main memory came in, where the CPU picks a process from the memory and executes. And then at the same time, the I/O device can pick from memory and input or output whatever it wants. It brings or to just be putting it into memory. Then there was also channels, right? Also channels. So what happens in the channel is that the CPU can pick from memory, and then the channel can pick from I/O devices into the channel and wait until when there is opportunity, it puts it in memory, pulls it out of memory, or then CPU can run. So this way, all ways of how can we speed up I/O so that things can come in faster while we're printing. All right. So the batch systems kept on going on with trying to see how we can get the I/O. How do we know that I/O has complete? That was another issue. Because now you're being automated, it wasn't handled by human beings again. So how do you know that the I/O has finished what it's supposed to do? Then there was what we call pooling. The device sets a flag when it is busy. And then the program tests the flag in a loop waiting for completion in a loop. The program tests the flag in a loop waiting for completion of the input output. All right. So what happens is that the program keeps testing. Keep testing. Is the I/O busy? Yes. If the flag is up, then it is busy. So wait for a while, come back again and test. So that was how it was doing. Pulling to see if whenever the I/O is free, now takes on. Then the second option was using interrupts. Right? Then that works was that on completion of I/O, the device forces the CPU to jump to a specific instruction address that contains the interrupt service routine. So once a process has completed this I/O, it forces the device, on completion of I/O, the device forces the CPU to jump to a specific instruction address that contains the interrupt service routine. After interrupt has been processed, CPU returns to code we were executing prior to servicing the interrupt. So interrupts were a way of getting the CPU's attention. But look, we have been working on this guy. There's another process that needs your assistance. So go over the source problem and come back and continue in this. Okay. So now after the batch issues, we still have a problem. Multiprogramming now came up. Multiprogramming now makes it better. Now here we're using interrupts to run multiple programs simultaneously. So here you can easily tell the CPU, jump to this program, run this program, after a while, stop, jump to this other program, after a while, stop, jump to this program. So we now have when a program performs the I/O, instead of pulling, execute another program till the interrupt is received. All right, remember that pulling was it has to keep on going to be looking, checking. I got I finished. But this one says that once the program has performed its I/O, instead of it to be checking if the device available, just jump to the another program until interrupt is received. When you receive an interrupt, you come back to this one. So the CPU instead of waiting for a process to finish its execution, then after executing, it goes to do I/O. and then finish everything before another program is taken. While it is doing I/O, CPU goes ahead to put another program. So here it requires pure memory. You have an I/O for each program. It requires intervention if the program looks indefinitely. Then it requires CPU scheduling to choose the next job to run. So we're going to discuss more on this in a multi-program environment. Then the concept of time sharing is very, very essential now with multi-program environment. We have the hardware. In this situation now, hardware is getting cheaper and humans are getting expensive. That's the thing now, because in time sharing, the programs are queued for execution in first out order. All right, like multi-programming or timer device. Remember, in multi-programming, once there's an interrupt, we go to service it. But here in time sharing, everybody has a time slice. You have a time slice, and once your time slice is up, they pull you out, and the next person takes over. So the timer device interrupts after a quantum time slice, a quantum time. So interrupted programs is returned to the end of the FIFO. FIFO is first in, first out. So interrupted programs return to the end of the FIFO, and the next program is taken from the head of the FIFO, right? So that was what was happening. When the control card interpreter replaced by command language interpreter. So they never had a control card interpreter. Now they're talking about command language. All right. So it was interactive. That's the beauty of time sharing. It's interactive. You have an action, you have a response. So when the operating system finishes the execution of one command, it seeks the next control statement from the user. That's what it does. So if it finishes execution of one command, time is up. It picks another, executes and fetches another program. So the file systems, look at file system, you have the online file system is required for users to access data and code. The online file system is required for users to access data and code. So the file system there, which is inbuilt, usually stored for data to be accessed, code to be accessed by the CPU. And or if users need it, you can also get it. Then we have the virtual memory. Now the job is swapped in and out of memory to disk. So during time sharing, we have to talk of the concept of virtual memory comes and we'll discuss more on virtual memory. So the job is swapped in and out of memory to disk. Virtual memory, remember, is the main memories where time sharing is working on, which is usually the RAM, the main memory. Now, we now go into personal computing, which we are right. Everybody has his own system, and here hardware is very cheap, but human beings are expensive. So we had single user systems, which were now portable. One could just get a laptop. Now we have phones, we have iPads, we move around, and you solve problems, use your word processors, your databases, and whatever. You get access to the emails and whatever you need. So we also have I/O devices where people have keyboards, mice, displays, small printers, and all that. Laptops, palm tops, cards, wireless devices. Single user systems may not need advanced CPU utilization or protection features because usually it's just used by you, so no need to protect much. The advantage are the user convenience, responsiveness, and it's ubiquitous. Use it anywhere you want. Then this is all about parallel systems. Now, parallel systems also came out as time went on. Parallel systems, multiprocessor systems with more than one CPU in close communication. Multiprocessor systems with more than one CPU in close communication. You have improved throughput, they're economical, they have increased reliability. So you could have a system, one system that has more than one CPU system, just one system has multiple CPU. And the CPUs perform different tasks. So you have multiple CPUs, they pick different tasks and they perform, and they end up being faster, right? Much faster. We have vector and pipeline parallel system, symmetric and asymmetric multiprocessing is involved. Then we hear concepts like distributed memory and shared memory. Then parallel programming brings up the issue of programming models. We have tightly coupled and we have loosely coupled programming models. Tightly coupled and loosely coupled programming models. We also have message-based and shared variable programming models, which we will discuss as course progresses. Look at a computing system here. The earlier two in Illinois here is where you have computers that had one computer that had multiple microprocessors, was used for climate modeling, liquid simulations, genome analysis, protein folding, and other things, other researches. Same thing with the K computer in Japan. Then we have the connection machine at MIT. And then we have IBM UG also. All of them used to do. Now, with as history went on, we now had the distributed systems. We have distributed systems. Distributed systems, hardware is very cheap, and then humans are very expensive. Here we have personal computers that are distributed everywhere and are connected to each other. So you have distributed computation among many processors because each device on its own has a processor. You don't need to share processors. You don't need to have multiple processors in one device. Now each device has a processor. And they are loosely coupled, definitely. No shared memory, various communication lines. Then we have the client-server architectures. For example, the websites. You can host your website on someone's server, or we could have a server where we have multiple clients connected over a local area network, a wide area network. Things like that came up. So the advantages of the distributed system was that resource sharing became better, easier. Computation was very fast, it was reliable. Communication was now easier. We could use things like email to send mails across. We could save data, and we could use software as a service. Lots of advantages. It's applied in digital libraries, digital multimedia, and diverse locations, social media networks, where we're using these systems right now. So we look at cloud computing offerings by many companies like Google, Sun, Amazon. They have lots of cloud computing services. We have global grid computing also, and right now, and that has encouraged us to have lots of advantages right now, making us have access to things that ordinarily we not had access to before. Then we have correct system function. Now let's look at the real-time systems, right? Real-time systems also came up as time went on. Remember, technology kept on getting advanced, and we needed instant response. For example, we have a plane here who's flying, and the plane is sending signals to a fellow plane, and wants to know its distance, its height from the other plane, its speed. So they can communicate and space themselves. We also have satellites talking to planes, and you want instant response because you can't send this kind of signal out and then you don't get response immediately. Then definitely there can be a crash if there's delay. So the correct system function depends on timeline, serious on timeline. So the plane must make sure that it gets a signal back immediately. So these are real-time systems. Feedback control loops, very essential. Chips That's how they dodge each other. They don't really necessarily have to chips on the water. Don't have to really see each other. And like sending radar signals across his path in front, we can know his distance from our ship from the shoreline. The plane can also know his height from the really consume it. So because of that, they are really applied in sensors and actuators. We have hard real-time systems and we have soft real-time systems. Now, in hard real-time systems, failure if response time is too long. You can have like in planes, response time cannot be too long. Immediately it needs signal to know if the sensor or not plane is the secondary storage is limited. Then in soft real-time systems, less accurate if response time is too long. Less accurate. For this way, you have multimedia, virtual reality. For example, we have here virtual reality system where people feel that they are drawn to maybe have an experience when you're watching a movie or you're playing a game. And as you move your hand, the picture also, your image moves as if you are in the game, you're moving by yourself. As you move forward, as if you are moving. That's real time and it's soft. So the system can catch up with your system. If you are faster than the system can always catch up with you and there is no crisis. All right. Now we are moved all over and then our computers are much faster right now. They're super and the interaction has changed. We have here we have super AMOLED displays. This OLED displays are very powerful. We have touch screen right now, capacitive touch screens. We have speaker, microphone, vibration, all of them inside our phones and all that, personal devices. We have sensing devices all in our phones. You have big computers big cameras in front and the back. We have accelerometer, gyroscopes, proximity sensors, compass, barometer, temperature sensors, lots of sensors all within these computers. We have GPS also that tells our location. We have also devices that are for connectivity, 4G, Wi-Fi, Bluetooth, infrared, and we also have those for acceleration. For example, we can extend our memory from 64 gig to more than 28 or more gig using micro SDs. We have faster GPUs for games, and we have multimedia processors also in just our little personal devices, our phones, and that. So the operating system has grown everywhere in digital watches, in our headsets. We even have Google like that. We have the Google eyeglasses. You have laptops and pads and all that everywhere. We have it now. Operating systems in vacuum washing machines. We have them in watches. We have them in speakers. We have them in shopping carts, in helmets. Lots of it. Even we have devices everywhere in our television sets, infotainment, and amazing everywhere, everywhere. So these are all the things that the president has really done and has made it very nice and interesting for you to have a operating system. So we have been able to study what an operating system is. We have looked at early operating systems. We have looked at simple batch systems, multi-programmed batch systems, time-sharing systems, personal computer systems, and parallel and distributed systems. Right. So these are some of the things we have discussed. Please, I would like you to drop any comments on any of the topics that what comment you have there on what we have discussed, what you want to add, suggest, what we should also add. Then you could also like and subscribe to the channel so that more people can see and understand how the operating system works. This is we'll see you in the next lecture. Have a Great day. So we'll see you in the next lecture.